This is Calculus 3 video lecture number 27 on vector fields, and we're beginning our new unit on vector calculus. This is basically the unit where everything in the course comes together. So just to recap, we've previously studied real valued functions of a single variable back in the day when we just were dealing with y as a function of x. So basically you could think of f as mapping from R1, one-dimensional real number space, into R1 again, right? Input was x, output was y. Then we started studying vector valued functions of a single real variable. So remember our vector valued function, we usually represented it with r of t, and each of the components was a real valued function. So the domain, the input for r was a single real variable. So we say that r would map from R1 into either 2 or 3-dimensional vector space, right? Our output was a vector. And then most recently, we've studied real valued functions of several variables where we dealt with w as a function of x, y, and z, or we also had z, which was just a function of x and y. So we could say that in this particular case, f would map, this f here would map from R3, right? The domain would be x, y, z in ordered triple into R1. Your output is a single real variable. All right, now we're going to study a new little beast called a vector field. So what exactly is that? That is a vector valued function of several variables. So now the domain is going to be in multidimensional space 2 or 3, and then the output is going to be in either 2 or 3-dimensional vector space. So it's almost like vector valued functions of a single variable and real valued functions of several variables made a hybrid. So here's our definition. A vector field on 2 or 3-dimensional space is a function f. Now notice here we use capital F and it's bold, right? Because it's a vector function that assigns to each point xy or xyz a 2 or 3-dimensional vector given by capital F of xy or f of xyz. And these vector fields are commonly represented in the following form. So each of the components themselves is a real valued function of several variables. So we can represent them with p of xy, q of xy, or in the case of a 3-dimensional vector, p, q, and r. Okay, where p, q, and r are scalar functions. Now, examples of vector fields you might have encountered previously include maps showing the direction and magnitude of winds or of a current in fluid flow. And we can sketch vector fields by drawing a few representative vectors where each vector, capital F of xy, is drawn with the initial point for the vector being whatever xy is. So let's try out an example here. We're going to sketch the vector field f of xy, which equals xi hat minus yj hat. So if you want to rewrite the vector field as just x negative y, and then play around with what sort of inputs you want to use for x and y until you get a feel for what's going on here. So let's see, I'll scale out maybe just to 5 in all directions. But until you start doing a few, it's hard to know exactly what you're going to need. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so 0, 0 won't be interesting, right? I won't get a vector out of that, so we're not going to waste our time. Let's see, let's try plugging in the ordered pair 0, 1. Then I would get the vector 0, negative 1. So what I do is I go to 0, 1. This is going to be my initial point. And then I draw a vector whose components are 0 and negative 1. So if I start at 0, 1 and the components are 0, negative 1, then the vector would just go back to the origin, right? What if I switched them around? F of 1, 0. Then I would have the vector 1, 0. Okay, so I'm going to start at 1, 0, that's my initial point, and then draw a vector with components 1, 0. Okay, interesting. What about f of 1, 1? That would have components 1, negative 1. Okay, so 1, 1 is my initial point, and then I draw it with components 1, negative 1. That would take me back down there. What about f of, let's go up a little bit, f of 1, 2. Now that takes me to 1, negative 2. So you're starting up here, and then now, since the y component is always the opposite of y, it's just going to send you right back down to the x-axis. What if I had f of 1, negative 1? Then I would end up with 1, 1. So if I start at 1, negative 1, again, I go back to the x-axis. And you don't have to necessarily plug them in. You can see the pattern of what's going on, right? What if I went out a little bit further? What if I plugged in maybe f of 3, 1? Then I would get the vector 3, negative 1. So 3, 1 would start here. Then I have the vector 3, negative 1. It would terminate back at the x-axis. And same thing, if I went up higher, then the y component would just be the opposite of y. It would send me back down there, etc. And then you can just mirror them on the other side because we know what's going on here. All right, and I'm just arbitrarily picking points until I get a feel for what's going on, what the pattern is, how the vector field's behaving. And it could take quite a few vectors until you get a sense of what's going on. Let's see what's happening on the other side of this graph. What about f of negative 1, 0? That would have components negative 1, 0. So f of negative 1, 0 has components, that's right, that the initial point's going to be right here, has components negative 1, 0. Now it's going away this way. Okay. F of 0, negative 1 would have components 0, 1. So starting here goes back to the origin. Okay, we got it, we got it. And then similarly, I know if I had f of negative 1, it would be negative 1, 1. Let's fix that. Oh. So negative 1 would send me back here to the x-axis. And then I don't have to keep plugging in. I know what's going to happen. It's going to look the same on the other side. If I had negative 1, 1, it's going to go back down. Same thing with 2. Okay, and you can copy some of this stuff on the other side if you're so inclined. All right. Now, as you can see, it's going to take a lot of work to get a good feel for exactly how this vector field is behaving. So frequently, we use technology, some sort of computer algebra system like Maple or Mathematica to draw vector fields. And this is particularly true for three-dimensional fields. As you can imagine, it would be very difficult to do that by hand. And in this case, the vectors are often scaled so that they're not going to be too long, but that they're just proportional to their true lengths. Because you can imagine, like for the example that we just did, if I started plugging in values for x and y, 20, 50, 100, right, then I'd have vectors that would be very long. The magnitude would be beyond what you could draw comfortably. So that's why they're scaled down when you use these technologies to graph. So here actually is a sketch that Scientific Notebook generated for the vector field that we just attempted to draw. And we were along the right track, but obviously you just need to keep working and filling in a lot more so that you can see. Let's compare. I think we did an admirable job, don't you? All right, let's try one more. So let's sketch the vector field f of x, y, which equals, now look at this, y over rad x squared plus y squared, and then the next component is negative x over rad x squared plus y squared. Now, obviously, it's going to be a little too painful to try to just start plugging in values. So we want to see, can we notice something about this vector field that's going to help us draw it more easily? And one thing I notice is they have the same denominator. So what if I were to factor that out, right? Because that's just a scalar, 1 over rad x squared plus y squared. And then now let's just focus on the vector part, y negative x. Well, what would be the magnitude of any vector here? Well, I would take the square root of y squared plus x squared, and then I would divide it by the square root of x squared plus y squared. So every single output from this vector field is a unit vector. They're all unit vectors. Interesting. So all of them have magnitude 1. Okay, say I started plugging in for x, y, just some arbitrary point. So I'm just going to consider, actually not an arbitrary point, a position vector. Let's consider the position vector x, y. So if I take that position vector and I dot it with any vector from this vector field, I don't need to worry about the 1 over rad x squared plus y squared. I'm just going to focus on y and negative x. Notice this dot product is 0. So any position vector is going to be orthogonal to the vectors yielded by this vector field. So what does that mean? Okay, let's draw a few position vectors and then draw vectors that are going to be orthogonal to it, whose magnitude are 1. That's what we're going to do. Okay, so here's x-axis, here's y-axis. All right. 1, 2, 1, 2. That should be enough. Okay, and I'm gonna just sketch little circles, with radius 1 and 2, just to give me a little bit of a guide as I'm graphing here. Okay, so pick some arbitrary position vector. I'm not graphing the vector field. I'm just going to pick some random position vector. Okay, so I'll say I'm going to graph this little vector right here. So that vector has components 0, 1. I know that my vector field, f of x, y, f of 0, 1, is going to spit out the vector 1, 0. Okay, so what does 1, 0 look like? Now I'm going to change colors because this is actually our vector field. It's like this. There's 1, 0. Notice they're orthogonal, right? So I don't need to draw these position vectors every single time. If I had another one, maybe it went here, right? Then I know the vector that results from this vector field is going to be orthogonal, and it's a unit vector. And notice the direction that they're tracing out is counterclockwise. And they're all going to be tangent to this circle. Okay, and then same thing on the outer. You can continue the process round and around. Okay, make sure they all have magnitude 1. And you can, to figure out that the direction was counterclockwise, you could just plug in a couple arbitrary values to determine that. All right, very good. Now, just some notation I wanted to point out. In vector fields, the notation, if you have a bold X with an arrow above it, that's a position vector. And it's often used to represent the point XY or XYZ. So we can also write f of xy as boldface f of the vector x, but x is really the point xy or xyz. That's just like an abbreviation for writing them out. Now, why are we studying vector fields? Well, there's so many applications, especially when you get into more physics. So some of the most popular applications include velocity fields as well as inverse square fields, such as gravity. And we actually have seen vector field functions before. You just didn't know it. Remember the gradient of f of xyz, which we denoted with that delta, was the gradient of f. So this meant that the gradient of f, which equals the partial with respect to x, partial with respect to y, partial with respect to z. Remember, we found it by taking the partial derivatives of our function of several variables. We took the partial derivative corresponding to each component. So what does this imply? That the gradient of f is a vector field, and it's often called a gradient vector field. Now, we categorize vector fields in the following way. We say that a vector field f is a conservative vector field if there exists a function, lowercase f, okay, real valued function, with f, the vector field, being the gradient of that lowercase f. So in other words, f, the vector field, is conservative if it is the gradient of some function f. All right, so a vector field is conservative if it's some other function's gradient, okay? And if it is a conservative vector field, then the function whose gradient it is called the potential function. So that lowercase f is the potential function. So if you take the gradient of the potential function, you get a conservative vector field. Now, later on in the chapter, we're going to develop techniques to determine whether or not a vector field is conservative. And that's something that we're going to be interested in because it's going to make several of our computations and problems a lot easier once we know that a vector field is conservative. Also, we want to know how the graph of a gradient field is related to the contour map of the function. Do you remember when we studied level curves and contour maps? So we're going to look here at our good friend, f of xy equals x squared plus y squared. Why do I call it our good friend? Well, this is z equals x squared plus y squared. Do you recognize this? This is a friendly paraboloid, right? So here's the contour map for it. So remember, if we were to draw the paraboloid out in space, just going to do a little rough sketch. You know, it opens along the z-axis. And so here's the level curves, right? One here, another one here. So we have these concentric circles centered at the origin. The gradient vector field is superimposed on the contour map. And we're asked here to just determine what this gradient vector field is. So let's go ahead and compute the gradient of f. Remember, it's partial with respect to x, partial with respect to y in this case. So it's going to be 2x and 2y. Now let's see if this matches the vector field that's drawn here. Notice in the first quadrant, both x and y are positive, and that matches the direction of the vectors that we see here, right? Both x and y components are positive. In quadrant 2, I would expect x component to be negative, y component to be positive, and that's precisely what we see here. Also, as we move further away from the origin, the magnitude of these vectors increases. Notice here, quadrant 3, both are negative, and in quadrant 4, x component's positive, y component is negative. And interestingly, they're perpendicular to the level curves. Yes? Very good. Now let's look at one last graph here. We have the contour map for the function f of xy equals sine of x plus y. And the surface is shown below right here. So this is the function in space, sine of x plus y. And we are asked now to find the gradient vector field for the function and then examine its sketch superimposed on the contour map. Okay, so the gradient of f is, remember, partial with respect to x, comma partial with respect to y. So if I take the partial derivative of sine of x plus y with respect to x, I'm going to get cosine of x plus y, and then derivative of x is just 1. And then same thing for the y component, interestingly. So that part's done. And then now we just have to Examine the sketch. Okay, let's start examining it. Now, one thing to notice, oh my goodness, I give up. Let's just box it with this highlighter and call it a day. One thing to notice here with this surface that's been sketched out is that the axes are oriented differently than how we typically draw them. Notice this is the x-axis, this is the y-axis, and 0's in the middle. Okay, so to kind of help you out, let's break it up. Here's our xy plane. No, it's not, because here's where z is equal to 0. So xy plane is sitting up higher, right? But where are x and y both positive? Right here. So this is where you would think of quadrant 1 in your mind. Okay, so you have to kind of turn things around in your head. And then this is where z is equal to 0. So just be careful. Okay, so here we see that the level curves are drawn, and then the vector field has been superimposed, and typically they come together nicely so that you can get a good idea for how functions are behaving as well as the vector field at the same time. Okay, so that concludes the lesson. Be patient while you're drawing the graphs. It can be a little bit tedious, and typically in application we use technology because it does such a superior job to anything we could do by hand. Stay tuned.